Hello and welcome to this session. In the last session, we studied equivalent circuit of a transformer. So this is the equivalent circuit of a transformer. You can see on the primary side, we have the resistance RP and the reactance XP. RP representing the resistance of the primary winding and contributing towards the copper loss in the primary winding. XP representing the leakage flux in the primary winding. Then you have RC and XM. RC representing the core loss component uh, due to hysteresis and eddy current losses, and XM representing the magnetization, the current that is responsible for the reactance that is actually responsible for production of magnetic flux in the machine that links the primary and the secondary winding. On the secondary side, you have resistance RS representing the secondary winding resistance and contributing towards the copper loss in the secondary winding. And you have the reactance XS representing the reactance owing to the leakage flux in the secondary winding. So this is about the equivalent circuit that we studied last time. Now, this equivalent circuit is not we usually do not use this equivalent circuit for analysis, for mathematical analysis, for studying the transformer in different networks, because we want to have a common electrical circuit representing both the primary, actually linking the primary and the secondary winding. To do that, the first step, we'll be actually studying approximate equivalent circuits today. In order to derive the approximate equivalent circuit, we have this circuit here first. It represents the same equivalent circuit that we have studied last time. Only difference here being is that the secondary side has been referred to the primary side. Fine. Or we can do what we can do also is refer the primary side to the secondary side. We have already seen impedance transformation. When we refer the secondary side to the primary side, the secondary resistance and the secondary reactance, that is RS and XS, they get multiplied by A square, where A is actually the turns ratio of this transformer, and obviously the voltage and at the secondary, at this terminal, will be AVS, and the current will be IS divided by A. This is when we refer the secondary side to the primary side. If we refer the primary side to the secondary side, RP and XP, they basically get divided by A square on the secondary side. So we actually obtain these are not approximate equivalent circuits. These are the same equivalent circuits that we have studied in the last lecture. The only difference being here is that we have clubbed the two electrical circuits into one by referring the primary side to the secondary side or the secondary side to the primary side. So the reactances and the resistances will exactly change. In case of referring the primary side to the secondary side, also RC and XM, they will get divided by A square. So now using this approximate equivalent circuit, using this equivalent circuit that we have derived from by referring the secondary winding to the primary winding, what we can do is we can now club RP and A square RS, and we can also club XP with A square XS. Now, how we can club these two resistances? It is owing to the fact that the magnetic current, that is the total excitation current actually, flowing through both RC as well as XM, whereas core loss current is flowing through RC and magnetization current is flowing through XM. This excitation current is very low. It is as low as we can say actually that the voltage drop because of the current flowing in our see the total current flowing in the excitation branch is leads to negligible voltage drop in both RP and XP. Because of this negligible voltage drop in RP and XP, what we can do is we can shift the shunt branch, we can shift RC and XM to the uh, towards the we can shift it towards one end. Uh, that means we can either have it in this fashion or we can have it in this fashion, where in one case we can see that the branch has been moved towards the primary terminal. In the other case, we can see that the shunt branch has been moved towards the secondary terminal, and the total resistance RP and A square RS, they form a net resistance now, that's R equivalent, and you have uh, XP plus A square XS forming a net equivalent resistance, that is X equivalent. So we can do this by shifting it to the primary winding either in case of a secondary winding being referred to primary winding or primary winding being referred to the secondary winding. That means we can shift the shunt branch towards the primary terminal or we can shift the shunt branch towards the secondary terminal. Regardless of that, we can actually club the resistances and the reactances to form these two approximate circuits now. These are not now the equivalent circuits of the transformers. These two are approximate equivalent circuits, and the fact here is that these two can be obtained of the uh, because of the fact that the excitation current is very low in case of a transformer. Now, having said that, what we can do is even in some cases where the excitation branch is, we can actually neglect it altogether, and the circuit that will obtain because of neglecting the excitation branch altogether is like this. Uh, so in this case, you can see that uh, there is no RC and no XM. So excitation branch may be neglected without causing any serious issue in some cases. This will not be applicable for all the cases, but in some cases. So we are now practically reduced our transformer to circuit where there is only one resistance and one reactance, and this can be sufficient enough for us to uh, for analyzing the behavior of this transformer. So this is about the approximate equivalent circuit of a transformer. So we can obtain an approximate equivalent circuit of a transformer by first referring the secondary winding to the primary winding or the primary winding to the secondary winding. Having done that, after that what we can do is we can shift the excitation branch either towards the primary terminal or towards the secondary terminal, owing to the fact that the excitation current is very low in magnitude and results in a voltage drop in RP and XP that's almost negligible. And in certain other applications, we can altogether neglect the excitation branch because of the current flowing through this branch is very less in magnitude, that it will not have a serious impact even if we neglect this branch at all, and therefore the equivalent circuit will reduce down to only one resistance and one reactance. So this is all about the approximate equivalent circuit of a transformer. Now after this we'll be studying the tests that we can do in a transformer. For this we'll be studying the open circuit test and the short circuit test in a transformer, and these tests are actually performed to obtain or determine the parameters of a transformer. So we may be given a transformer. You can take any transformer that's actually used in residential applications. We do not know the value of the primary winding resistance. We do not know the value of the leakage reactance of the primary winding or the secondary winding. We do not know the resistance of the secondary winding. So how to determine these values? How to determine RP? How to determine XP, XS, L, XM, or RC in case of a transformer? So for that uh, we can perform various tests, various operations. The first one is the open circuit test. So in case of an open circuit test, what we do is the features of this test are In case of an open circuit test, the primary winding is uh, rated voltage is actually applied to the primary winding. Primary winding is excited through rated voltage. The primary winding is excited via it's actually a rated voltage is applied to the primary winding of the transformer. After this, the secondary side is kept open. The primary winding is excited via rated voltage, and the secondary side is kept open. That means no load is actually applied to the transformer. And using this circuit that is shown here, we can actually measure the value of primary current. We can measure the value of voltage applied to the primary winding. We can also measure the We have also connected a wattmeter here to measure the power flowing in the primary winding. Now, once we perform this test, you can look at the circuit. Since no load is applied to the secondary winding, IS is practically theoretically zero. So all of the current that's actually flowing right now, it is contributing towards only the core loss and the magnetization current. So you can say that the current actually this time I once we actually performing an open circuit test, uh, all of the current is concentrated towards the core loss component. So the power that actually will be obtaining in this case will be the core loss power. So what happens in this case is that the current flowing in the primary winding now will be very small, because all of this current is actually contributing only to the core loss current and the magnetization current. And since we have already said that the excitation current is very low, so all of this current flowing in the primary winding right now is only the excitation current, and excitation current is very low. RP and XP of a transformer are usually much lower as compared to RC and XM. So we can say that the voltage drop in RC and XM, that will also be low, and the voltage drop in RC and XM will only be uh, that the voltage drop in RC and XM will actually be the input voltage. The input voltage will actually be contributing to the voltage drop in RC and XM, while the voltage drop in the primary resistance and the primary reactance will be very low, so that we can actually neglect them. So we can actually determine the shunt parameters using the open circuit test. And that also means core loss can be determined using this. So in case of an open circuit test, the secondary side is open. There is no load, so IS is practically theoretically zero. So all of the current flowing in the primary winding is only excitation current. Excitation current being very low, RM and RP and LP XP already being very low, we can say for sure that the voltage applied to the primary winding is mostly concentrated in the shunt branch, that is RC and XM. Now we can actually find out the value of RC and XM by first of all finding the admittance. Admittance will be given to us using IOC divided by VOC. Uh, so IOC, where IOC is the current flowing in the primary winding during open circuit test. VOC is the voltage applied to the uh, VOC, the voltage applied in the open circuit test. So this actually gives us admittance. We know admittance is equal to G minus JB, where G is conductance and B is susceptance. So we can also say this G in this case will be GC and BM. That means this is actually 1 by RC minus 1 by plus 1 by JXM. Fine. So if we now know the value of IOC and VOC from the measurements we take from ammeter and voltmeter, we'll get to know the value of this complex voltage, and also we can find out the power factor in the system. We know the power in the system is POC, that is actually determined using the wattmeter, and dividing it by VOC and IOC gives us the power factor, that is actually cos theta. So which implies theta will be equal to cos inverse of POC divided by VOC into IOC. POC is the wattmeter readings that we will take while actually determining this experimentally. VOC is the voltage that will be applying experimentally. IOC is the ammeter reading that we can take. So we know POC, VOC and IOC. So we can determine theta from here. If we know the value of theta and we actually know the magnitude of IOC also using this equation, IOC divided by VOC, we can get to know the magnitude of 1 by RC and 1 by XM, and to find out the value of theta to get the complete YOC, that's actually angle YOC and this angle theta. So this will give us the total admittance of the circuit, from which we can find out 1 by RC and 1 by JXM. That means actually we can find out RC and JXM by calculating this value of admittance. Fine. Since it will be a complex quantity, like say for example YOC is equal to 3 plus 4i whatever, so 1 by RC will be 1 by 3 and 1 by XM will be 1 by 4i, 1 by 4. So that will be the value of RC and XM determined using the open circuit test. Now in case of a short circuit test, what we do is we short in case of short circuit test, we short the LV winding. I'm not now saying the primary winding or the secondary winding. I refer to this specifically as the LV winding because we'll make sure and apply voltage through HV winding. So we'll short the LV winding in this case and we'll apply the voltage through the HV winding such that rated current flows through it. We specifically perform the test in this manner so that we can short the LV winding and apply the voltage to the HV winding, because we do not want, because since we are shorting the winding, large amount of current will be flowing, so we do not want a significantly large amount of current to flow. So we'll perform this test by making sure that the LV winding is shorted and not the HV winding. So this, and we make sure that we actually perform this test very quickly so that the transformer does not burn down. So what happens in this case is that even if you apply 30-40 volts only, already the rated current will be flowing because the secondary side, the LV side will be shorted in this case. That means actually this is full load. This can be referred to as full load condition. Fine. So even at very low voltage, that's only a 30 or 40 volts, rated current will begin to flow in the transformer. So considerably lesser amount of voltage In case of open circuit test, you might have been performing the test at 230 volts or 440 volts. But in case of short circuit test, you are only applying 30, 40, 50 volts, 80 volts, something like that. So even at low voltage, you are performing this test at low voltage. Since voltage is low, the voltage across the primary, that's across the parallel branch, across the shunt branch, will also be low. And since the resistance is very high of RC and XM, the current flowing through RC and XM will be in this case negligible. That will be totally uh, almost approximately zero. So we can actually neglect the shunt branch in this case. So what this will give us will be the series parameters. And the series parameters in this we know are RP and RS, XP and XS. So RP and RS, they are actually contribute to the copper losses in the system. So copper losses can be determined using this test. So you can say ZSC is equal to VSC divided by ISC, where VSC will be the voltmeter reading at short circuit, ISC will be the ammeter reading at short circuit, and this in this case will be equal to R equivalent plus J equivalent. Fine, not RP, because this will be R equivalent, where R equivalent will be Rp plus Rs, not Rs, actually A square times Rs, and X equivalent will be Xp plus A square Xs. Fine. So using the knowledge of impedance from the measurements of voltage and the measurement of current from the voltmeter and the ammeter, we can calculate the impedance, and from there we can then this will actually be the magnitude of this. To determine the theta, again Pf will be equal to Psc divided by Vsc into Isc, which is equal to actually cos theta. That implies theta is equal to cos inverse of Psc divided by Vsc into Isc. So Zsc will be equal to Zsc angle theta, that we can determine from here. So using the open circuit test, you can determine the shunt parameters because of negligible voltage drop across the uh, resistance Rp and Xp, and also we can determine the core losses using the open circuit test, whereas in case of short circuit test, we can determine the series parameters, and copper losses can be determined using these two tests. So these here are once again I'm showing you the circuit diagram of the open circuit test as well as that of the short circuit test. So if we know the value of the turns ratio, we can find out that we knowing the value of R equivalent, we can be able to approximate what will be the total series impedance and the total series reactance of this transformer. So this is about the test of these two transformer. We'll be doing a numerical